Alright, here's a quick video tutorial about the lab, the heats of combustion lab, because it requires a bit of calculation, so I figured you guys could use a little tutorial about it. So I've got the Google Doc here, and I'm in my Pivot Interactive, so get that set up. One thing to do here, because there's some tables to fill in. One thing that I'd really suggest, if you don't want to remake the tables yourself, just go here and go make a copy. You can copy the document, and then it'll copy it to your own Google Docs. Now you can edit it yourself, because I've got it set to view only, so we're just going to work with our copy. And then you can just submit that to our thing. So I'm going to do this with pentanol. You guys have to do the entire thing with anything but pentanol. So I'm going to do the one for pentanol. Here it is, pentanol. Yeah, let's get started. First question: choose an alcohol and write which one you choose. Well, I chose pentanol because I'm allowed to do that because I'm the teacher. Advance the video until the can is on top of the flame. Note the starting mass. Okay, well, easy enough. Play the video. Yeah, they stirred a little bit. So you see, the reason I say to wait until it's on top of the flame, in fact, I'm going to move this over to the right and take away my old topic and my learning goals. All right. The reason I say to wait until the can is on top of the flame is because notice that this goes down until the candle goes on there, until the can goes on there. So you want to stop it probably right about there. Right now the heat is going to go up into the can. So I see 85.062. 85.062 grams. Right? We always want our units. Maybe stick that in the center. Okay, ending mass. Right, until the can is taken off the flame. Same reason, we don't want to get the mass at the end of the video. We want to get it when the can is taken off the heat. So go forward till it's taken off the heat. See, now they're taking it off the heat. If we right about there. So 84.696, 84.696, 84.696 grams. Okay, determine the change in mass. Determine the change in mass. Well, gee, how do I do that? The mass changed by 84.696. 0.366 grams. So what I want you guys to do is actually write it out, because we have to write out our equations when we do a lab. We want our lab reports to be reviewable so that people can see what we did. And always the units, always keeping those units in there, 0.366 grams. Yeah. Determine the molecular weight of your alcohol. You can use a periodic table to calculate it, in which case we write out the calculation below. We can do that. I grab a periodic table of the elements, and I'm just going to write it out. So pentanol is C5H11OH. Right? C5H11OH. So we have 5 carbons. 5 times, and look at my table here, 12.01 grams per mole equals 5 times 12.01, 60.055 grams per mole. I'm going to do the rest of them and then pause and unpause. And so I finished it, 5 carbons, 12 hydrogens, 1 oxygen, add them together, I get 88.1488 grams per mole. Or you could just look up the the molecular weight in some kind of database like the NIST chemical database, pentanol. So there we go, the NIST web book, pentanol. There it is, 88.1482. Oh, hey, look, it's pretty close to what I got. If you do just decide to look it up, make sure that it's a source that's, authoritative. NIST is definitely authoritative, or PubChem is another option, and you're going to have to cite that. So give a little, brackets, NIST, blah, blah, blah. So yeah, get that total. Okay, we have to use the mass change in the molecular weight to determine how many moles of alcohol were burned during the experiment. Oh, look, it's stoichiometry. We're back to grade 11 chemistry. We have 0.366 grams burned, and 1 mole of it is 88.1488 grams, right? 88.488 grams per mole. So let's think about, do we have more than a mole or less than a mole? Well, it takes 88 grams to make 1 mole of this stuff. We burned less than 1 gram, so we're going to have a very small number. And so we're going to have to divide. We're going to have to divide 0.366 grams. Is it 366? Yes. Divided by 88.1488 grams per mole, and that's equal to, I'm just going to put some brackets around here just to make it look better. And divide by that many grams per mole, and that's going to be equal to some very small number. So 0.366 divided by 88.1488, I get 0.00415. There's some other numbers there like 415207, but if we think about significant digits, we only have 3 significant digits here. We're going to keep 3 significant digits there. And our unit here is moles, right? Grams per mole, grams divided by grams per mole gives us just straight up moles of C5H11OH. So yeah, that's how we figure out how many moles we have. Okay, now we're going to figure out the energy. Note that we can figure out the energy without needing any of this stuff. This is 2 separate things. The weight and the heat are actually 2 separate things. We're going to put them together later. So you can actually do part 2 before part 1 if you feel like it. It doesn't really matter. Okay, determine the energy absorbed by the water. First, we have to note how many milliliters there were at the start. Just under 500. That's 450 is there, and then it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 20 divisions. It's plus or minus 5 mils. We might as well just call that 500 mils. 500 milliliters. Convert it to grams of water. Well, water at normal temperatures is 1 gram per milliliter. So we're going to say 500 grams. Starting and ending temperatures of the water. So the water starts at, they're going to put the water in the can. They're going to stir it around a little bit. We're going to wait till this settles out to a specific temperature. 20.1. So 20.1 degrees Celsius. Start 20.1 degrees Celsius, and let's figure out the end. Just jump right to the end of the video, because at the end of the video they're just stirring the thing. Looks like it's 25.2. 25.2 degrees Celsius, and I'm just cheating and using the O as my degrees sign. Change in temperature of the water. Remember that when we use specific heat, it's the change in the temperature that we care about, the change. So it started at 20.1, it ends at 25.2. 25.2 degrees Celsius minus 20.1 degrees Celsius is equal to 5.1 degrees Celsius. I don't even need a calculator for that. It's pretty straightforward. right? And we've got to keep our units. So yeah, 5.1 degrees Celsius. Technically plus 5.1 if we wanted to do that. Hey, information above and the specific heat of water determine the total amount of energy absorbed by the water. Well, our equation is Q is mc delta T. I need a delta sign. Here's how I always get a delta sign. Like, I just always do this. I just search delta symbol into, and I just copy that. And I stick it in here. Now, if you go Control V, it becomes a big. If you paste, it becomes too big. But Control Shift V, oh no, Control Shift V gives you the normal one, delta T, MC delta T. Okay, and then we have all of this, right? M, the mass of water is 500 grams. 500 grams. C of water is given, 4.184 joules per gram degree Celsius. And times the change in temperature plus 5.1 degrees Celsius. Put it through a calculator, 500 times 4.184 times 5.1. I get 10,669.2. And then I need a unit. What's my unit for my energy here? Well, we had joules per gram degree Celsius. Grams will cancel grams. Degrees Celsius will cancel degrees Celsius. It's going to be in joules. So it's going to have in joules. Joules. Or, because that's a big number, let's take it to kilojoules. Let's divide it by 1,000 and make kilojoules. 10.7 kilojoules. We'll just have it. We'll just have it be 10.7 kilojoules. Or, 10,000 joules. Okay, so that's done. Next up, now we don't need the video anymore. We're just determining the heat of combustion from our kilojoules and our moles. We have our moles. We have our kilojoules. Determine the heat of reaction in kilojoules. So the water gained 10.7 kilojoules. So the chemicals lost 10.7 kilojoules. Right? The Q of the reactants then, the Q, which is the heat of the reaction, is equal to negative 10.7 kilojoules. Right, and now I have to figure out in kilojoules per mole. We want to figure out delta H, and that's going to be kilojoules per mole. So we have our kilojoules, we have our number of moles, so we have negative 10.7 kilojoules for 0.00415 mole is equal to, and then we just divide them by each other. Right, so negative 10.7 kilojoules divided by, big J for joules, negative 10.7 kilojoules divided by 0.00415 mole is equal to negative 10.7 divided by 0.00415 negative 2,578 kilojoules per mole. And what I'm going to do is I'm just going to round it to the lowest single digit there. Just leave it at that. I'm not going to do any significant digit type stuff. Technically, this should be 3 significant digits, and it should be minus 2580, and even that is not correct because we only had 2 sig digs on our temperature. But you know what? Good enough. Good enough to get some answers. So that's how you do just one. You get the kilojoules per mole for just one of these. In your task, note that I I should change that to 7.8. Note that you have to do this for the other alcohols, all 4 of these. You only have to do this whole write-up piece that took me 15 minutes for one of them, and then you just have to calculate the other ones. You don't have to do the full write-up or anything like that, but do give me the full thing. Here's the measured values from the database, from the NIC database. If I go here, 1-pentanol, and I go condensed phase thermochemistry data, it'll actually give me the heat of combustion here at minus 3330, minus 3000, where I got minus 2578. You're going to talk about that in the discussion section about whether it's higher or lower. And the last piece here, it was going to be, might be confusing for some people, is to turn it into kilojoules per gram instead of kilojoules per mole. I'll leave that to you guys. It's a little exercise in unit cancellation and figuring out how to get to kilojoules per gram. It's really not that bad. Yeah, that's the whole tutorial. Hopefully it helps you with the math of this lab. Yeah, thanks for paying attention.